You're scrolling through your phone, maybe lying in bed when you accidentally drop it. It falls maybe 3 feet and you watch it tumble toward the floor. That feeling in your stomach, that little drop of regret as you realize you should have held on tighter. Now imagine that feeling, but you're not dropping your phone. You're dropping yourself into the most extreme gravitational wells in the universe, into black holes, every type of black hole. And I'm about to tell you exactly what happens to your body, your atoms, and your last thoughts as you fall into each one. Okay, wish granted. But we're not just throwing you into one black hole and calling it a day. That would be too easy, too merciful. We're going to experience every single type of black hole known to science, from the smallest theoretical ones to monsters so big they could swallow 1,000 solar systems. And yes, you're going to experience very different and creative outcomes in each one. Some quick, some slow, all absolutely fascinating from a physics perspective. Let's start small. Really small. We're talking about primordial black holes. Theoretical objects that might have formed right after the Big Bang. These things could be smaller than an atom but pack the mass of a mountain. Picture this. You're walking down the street and suddenly there's this imperceptible point in space pulling at you. You don't see it. You barely feel it at first, but then your feet start to feel heavier than your head. Way heavier. Here's what's happening. The gravitational difference between your feet and your head, just 6 feet apart, is becoming extreme. We call this tidal forces, and with a primordial black hole, these forces ramp up incredibly fast. Your feet are being pulled thousands of times harder than your head. The technical term is spaghettification, and it's exactly as pleasant as it sounds. Your bones start to separate. Your spine stretches like taffy. Every ligament in your body is being pulled apart at the molecular level. But here's the thing about primordial black holes that makes them especially interesting. Because they're so small, the event horizon is tiny. From your perspective, you might see it as just a point of absolute darkness, smaller than a grain of sand. But the gravity gradient is so steep that by the time your feet cross that boundary, your head is still processing what's happening. You'd experience this strange time dilation where your feet are already beyond the point of no return, while your brain is still firing neurons trying to understand why everything hurts so much. The entire process, from first feeling the pull to being completely stretched into a stream of atoms, would take maybe 2 or 3 seconds from your perspective. From an outside observer's view, though, you'd appear to slow down as you approach the event horizon, your image getting redder and dimmer until you just fade away, frozen at the edge forever. But you wouldn't know that because you'd already be converted into the most elongated version of yourself physically possible, compressed down to a width smaller than an atom but stretched across meters. Every atom that was once you is now part of the black hole's mass. At least it was relatively quick, right, Kyle? You barely had time to regret your life choices. Oh, you think atom-sized is too small? You want something more substantial? Let me introduce you to Cygnus X-1, one of the first stellar mass black holes ever confirmed. This beast has about 21 times the mass of our Sun. Compressed down into an event horizon, roughly 40 miles across, that's more like it, right? Something you can actually see, or rather, something you can see the effects of because the black hole itself is still perfectly black. But here's what you notice first as you fall towards Cygnus X-1. The heat. Intense, overwhelming heat. See, this black hole is actively feeding. It's pulling matter from a blue supergiant star companion, and all that material forms an accretion disk around the black hole. This disk of gas and dust is spinning at a significant fraction of light speed, and it's hot. We're talking millions of degrees. Before you even get close to the event horizon, you're flying through this disk. The radiation hits you first. X-rays, mostly, which is why it's called Cygnus X-1. These aren't the medical X-rays you get at the dentist. These are high-energy photons that punch through your body at the cellular level, shredding your structural makeup. Your skin would begin to char almost immediately, but you're moving fast, falling faster and faster, so you punch through the disk like a meteor through atmosphere. Except you're not burning up, you're being ionized. Every electron in your body is being stripped away by the intense radiation. You're no longer flesh and bone, you're plasma, a cloud of charged particles that used to be you. And you're still falling. The accretion disk is behind you now, and ahead is just darkness, but the tidal forces are building. With a stellar mass black hole like this, spaghettification happens over a longer distance than with primordial black holes, which means you get to experience it more thoroughly. Your body starts to stretch. Your feet are accelerating faster than your head. The difference in gravitational pull between your feet and head becomes painful, then excruciating, then beyond pain into something your nervous system can't even process anymore. As you cross the event horizon, something bizarre happens from your perspective. You look back and see the universe blue-shifted and compressed into a shrinking circle behind you. Time is passing faster out there. Stars are being born and collapsing in what seems like fast forward, but ahead of you, there's only darkness. You're now inside the black hole, falling toward the singularity at the center, and the tidal forces are still increasing. Whatever remained of your structural integrity is being shredded down to the atomic level. Your atoms themselves are being pulled apart. Electrons torn from nuclei. Protons and neutrons separated. And then you hit the singularity. What happens there? Nobody knows. The math breaks down. General relativity predicts infinite density and infinite curvature of space-time, which means the equations stop making sense. Maybe you're crushed to a point of zero volume. Maybe you're spread across the surface of the singularity. Maybe you tunnel through to another universe. But probably, most likely, you just stop existing in any meaningful way. The information that was you is now encoded somehow in the black hole's event horizon, according to some theories, but you as a conscious entity are gone, thoroughly and completely gone. It took what, maybe 10 seconds from your perspective? Not bad. Quick enough that your brain didn't have too much time to process the horror, but we can do worse or much worse. What if instead of falling into a stationary black hole, you fell into one that's spinning? Let me tell you about Kerr black holes. Named after physicist Roy Kerr, these are rotating black holes, and rotation changes everything. When a black hole spins, it drags space-time around with it in a phenomenon called frame dragging. Near a rotating black hole, it's impossible to stay still. Space itself is rotating, carrying you along with it, whether you want to go or not. Let's say you're falling into a stellar mass Kerr black hole spinning at 90% of the maximum possible rate. As you approach, you enter a region called the ergosphere, outside the event horizon, but inside a boundary where frame dragging is so intense that you're forced to orbit the black hole. You're being spun around like you're caught in a cosmic centrifuge. The centrifugal forces combine with the tidal forces, and your body is being simultaneously stretched lengthwise and compressed radially. You're being turned into a very thin, very dense ribbon spiraling around the black hole at a good fraction of light speed. The radiation is more intense around a spinning black hole because the accretion disk is more energetic. Material in the disk can orbit closer to the event horizon when the black hole is spinning, reaching higher velocities and therefore higher temperatures. You're being cooked, ionized, and shredded by forces trying to tear you in multiple directions simultaneously. It's like being in a blender and a taffy puller at the same time while also being microwaved. But here's where Kerr black holes get really weird. In theory, a maximally rotating black hole could have a ring singularity instead of a point singularity. And in the mathematics, there's a possibility, purely theoretical mind you, that you could pass through this ring and emerge somewhere else. Another region of space-time, maybe another universe. Of course, The tidal forces would have already disintegrated you down to subatomic particles long before you reached the singularity, so this is kind of a moot point for your survival. But it's a fun thought. You're not just experiencing linear death. You're experiencing rotational death with a side of potential interdimensional travel, if only you weren't already quantum foam. Tired of stellar mass black holes? Kyle, you want to go bigger? Say hello to Sagittarius A, the supermassive black hole at the center of our galaxy. This monster has about 4 million times the mass of the Sun. The event horizon is roughly 17 times the diameter of the Sun. At this scale, something counterintuitive happens. The tidal forces at the event horizon are actually weaker than with smaller black holes. Wait, weaker? How does that work? It's because tidal force depends not just on the total gravity, but on how much gravity changes over a distance. With a supermassive black hole, the gradient is gentler. The gravitational pull at your feet versus your head is much more similar than it would be at a smaller black hole. This means you could, theoretically, cross the event horizon without being immediately torn apart. You'd be falling, accelerating, but relatively intact. You might not even notice the exact moment you cross the point of no return. That sounds better, right? Finally, a black hole that doesn't immediately shred you. Well, here's the thing. You're still doomed, just more slowly. As you fall deeper into Sagittarius A, you look back and see something extraordinary. Because of time dilation, you're watching the entire future of the universe play out in fast forward. Stars are forming and going supernova in seconds. Galaxies are colliding. If you fell in at the right angle and could somehow survive long enough, you might see the heat death of the universe itself in the last moments before the tidal forces finally become strong enough to pull you apart. Because that's the thing about supermassive black holes. The tidal forces are weaker at the event horizon, but as you fall toward the singularity, they still increase. Eventually, maybe minutes into your fall from your perspective, the forces become extreme. Your body starts to stretch. Bones separate. Organs rupture. You experience the same spaghettification as before, just delayed. And you had all that time, minutes of falling through absolute darkness, knowing it was coming. Knowing that no matter what you did, you were heading toward a singularity that would reduce you to your component quarks. Some might argue that's worse than instant obliteration. Having time to think about it. Having time to regret every decision that led to you falling into a black hole with the mass of 4 million suns. But hey, at least you got to see the future of the universe before you ceased to exist. Think that's big. Oh, Kyle, we're just getting started. Let me tell you about Cygnus X-1. This is an ultramassive black hole, one of the largest ever discovered. 66 billion solar masses. The event horizon is 1,300 astronomical units in radius. For context, Pluto orbits at about 40 from the Sun. You could fit our entire solar system inside this. Black holes event horizon 32 times over. At this scale, the tidal forces at the event horizon are so weak that you genuinely wouldn't notice crossing it. You'd be falling? Sure. But you'd be comfortable. Alive. Confused about why you're falling into darkness but not experiencing any immediate physical distress. You could survive for hours inside this black hole before the tidal forces became problematic. Hours of falling through the most extreme environment possible while your body just keeps working like everything is normal. But here's what makes Cygnus X-1 uniquely terrifying. The accretion disk. This black hole is actively feeding, and the amount of energy being released is staggering. The accretion disk shines with the brightness of about 140 trillion suns before you even get close to the event horizon. While you're still millions of kilometers away, you're being bathed in radiation that makes the surface of any star look cold by comparison. The light is so intense it's not visible light anymore. It's extreme ultraviolet and X-rays, and it's hitting you from every direction because the disk is so enormous. Your body would be heated to thousands of degrees in moments, your water content flash-boiled away, your flesh charred to carbon, your bones heated until they crack and shatter from thermal stress. And you're still conscious for the first few seconds of this, your nerve endings sending pain signals that your brain interprets as every cell simultaneously being on fire. Because they are. You're being cremated by starlight while falling into a void. By the time you actually reach the event horizon, assuming anything remains that could be called you, you're already thoroughly sterilized by radiation. And then you get to spend hours falling through darkness, a charred skeleton, slowly being pulled apart by tidal forces that increase so gradually you might not notice them, ramping up until suddenly your femur snaps in half and you realize, oh, right, I'm still falling into a singularity. You thought we were done? You thought that was as extreme as it gets? Let me tell you about charged black holes. These are theoretical. Probably don't exist in nature because black holes tend to neutralize any charge pretty quickly, but the mathematics allows for them. Reissner-Nordström black holes with electrical charge. A charged black hole changes the game entirely. Instead of one event horizon, you get two, an outer horizon and an inner horizon, and between them, there's this bizarre region where the geometry of space-time gets weird even by black hole standards. If you fell into a charged black hole, you'd cross the outer horizon just fine. Still doomed, still falling, but okay for the moment. Then you approach the inner horizon and things get strange. There's a phenomenon called the mass inflation instability. Basically, as you approach the inner horizon, you'd encounter a wall of radiation. Every photon that ever fell into this black hole, all the radiation that's been accumulating, gets blue-shifted to infinite energy right at the inner horizon. You'd be hit by what amounts to an infinite amount of energy in an infinitesimally short time. Not just annihilation. You'd be destroyed at a level that makes nuclear fission look gentle. And if somehow, theoretically, you survived that, past the inner horizon, the mathematics suggests you might be able to avoid the singularity entirely. The singularity in a charged black hole is theoretically a circle or ring, not a point, and the space-time geometry might allow you to pass through it into a region of negative mass or into another universe. Of course, you're already a spray of elementary particles at this point, having been hit by infinite energy, so your sightseeing opportunities are limited. The astrophysics community mostly agrees these probably don't exist. Black holes accumulate opposite charges too readily. But mathematically, they're allowed. And if you fell into one, you'd experience something that goes beyond normal black hole destruction into truly exotic territory. Okay. I might be getting a little carried away here. You know what happens when I forget to take my medication. Let's try something different. What if instead of falling into a black hole, you were expelled from one? What if you emerged from a white hole? White holes are theoretical time-reversed black holes. While nothing can escape a black hole's event horizon, nothing can enter a white hole's event horizon. They only emit matter and energy. If they exist, which they probably don't, but if they did, and if you somehow emerged from one, you'd be shot out into space at relativistic velocity. We're talking 99% the speed of light. You'd be a kinetic projectile with the energy of millions of nuclear weapons. Any planet you hit would experience an extinction-level impact event. Any star system you entered would have its trajectories perturbed. You wouldn't be a person anymore. You'd be a weapon of mass destruction. And here's the fun part. From the perspective of the universe you're entering, you'd appear without cause. One moment nothing, the next moment a highly energetic object violating causality. The universe doesn't like that. There would probably be some kind of feedback effect, maybe the white hole becoming unstable and exploding, taking you with it. You'd go from being ejected to being vaporized in the resulting energy release that would briefly outshine entire galaxies. So yeah, even the theoretical alternative to falling into black holes results in your thorough and complete destruction, just with extra steps and collateral damage. But we're not done with exotic scenarios. Let's talk about what would happen if you fell into a pair of black holes that are in the process of colliding. This happens. LIGO has detected gravitational waves from dozens of black hole mergers. Imagine you're unlucky enough to be between two stellar mass black holes spiraling into each other, and you're caught in the middle. The gravitational waves would hit you first. These aren't like ocean waves, they're ripples in space-time itself. As they pass through you, space itself compresses and stretches rhythmically. Your body would be squeezed and stretched by the fabric of reality oscillating. At first, maybe it's subtle, uncomfortable, but as the black holes get closer, the amplitude increases. The frequency increases. You're being subjected to space-time itself vibrating at hundreds of times per second. Your bones would fracture from the stress. Your organs would experience shear forces as different parts of your body are in slightly different phases of the gravitational wave. Your blood would have trouble flowing as vessels are compressed and dilated faster than your heart can compensate. And this is all happening while you're also being pulled toward both black holes simultaneously. You're experiencing tidal forces from two different directions, trying to stretch you toward both singularities at once. As the black holes get closer to merging, the gravitational waves become so intense that matter itself starts to behave strangely. The atomic bonds holding your molecules together are being stressed at the quantum level. And then the black holes merge. In a fraction of a second, they combine into a single, larger black hole. The merger releases more energy in gravitational waves than all the light emitted by all the stars in the observable universe combined for that brief moment. You're at ground zero for this. The gravitational wave pulse that passes through you is so intense it would rip you apart at the subatomic level. Quarks separated from quarks. The fundamental particles that make up protons and neutrons are torn from each other. You're not just killed, you're unmade at the most fundamental level physics allows. And then what's left gets absorbed into the new, merged black hole, which settles down and radiates away the excess energy as it stabilizes into its final form. From an outside observer's perspective, the entire event from merger to stabilization takes maybe a tenth of a second. That's how long you existed between two colliding black holes before being deleted from reality. So yes, you've been spaghettified, ionized, cooked by radiation, stretched by tidal forces, compressed by gravitational waves, and unmade at the quark level. Multiple times. In multiple scenarios. Each one a different way the universe has devised to thoroughly and completely end your existence. But here's the thing that should actually terrify you, Kyle. All of these black holes we've talked about, except the theoretical ones, they exist right now. Cygnus X-1 is out there, about 6,000 light-years away. Sagittarius A star is at the center of our galaxy, 26,000 light-years from Earth. Ton 618 is billions of light-years away, but it's real. It's there, actively consuming matter and shining with the light of trillions of suns. And the universe keeps making more. Every massive star that goes supernova has the potential to create a new stellar mass black hole. Supermassive black holes are at the centers of most large galaxies. They're not rare cosmic oddities, they're fundamental structures of the universe. There are probably millions of stellar mass black holes in our galaxy alone. Most of them are quiet, not actively feeding, invisible except for their gravitational effects. The closest known black hole to Earth is about 1,500 light-years away. That's essentially our cosmic backyard. Now, before you panic, we're not in any danger. Space is big, really big, and the odds of Earth encountering a black hole are vanishingly small. But they're out there, waiting, patient, ready to thoroughly demonstrate what happens when matter encounters the most extreme gravitational fields the universe can create. So the next time you drop your phone and feel that little moment of stomach-dropping regret, remember, it could be so much worse. You could be dropping yourself into any one of countless black holes scattered across the universe, each one ready to stretch, compress, ionize, and ultimately disintegrate you in ways that are perfectly consistent with known physics but absolutely horrific from a biological perspective. Sweet dreams, Kyle.